Hello, folks. All right. So, in today's lesson, I want us to look at um, electrostatics, grade 11 electrostatics, right? And before we do that, I just want you to recall these two important principles: the principle of quantization and the principle of conservation of charge, right? Yeah. Okay. In grade 10, you learned about the force between charges. In this chapter, you will learn exactly how to determine this force and about a basic law of electrostatics. These are some key mathematics concepts that you need to know: ratio and proportion, equations, units and unit conversion, and scientific notation. All right. Okay. So we'll start with Coulomb's law. Like charges repel each other while unlike charges attract each other. If the charges are at rest, then the force between them is known as the electrostatic force. The electrostatic force between charges increases when the magnitude of the charges increases or the distance between the charges decreases. The electrostatic force was first studied in detail by Charles Augustin de Coulomb around 1784. Through his observations, he was able to show that the magnitude of the electrostatic force between 2 point-like charges is inversely proportional to the square of the distance between the charges. He also discovered that the magnitude of the force is proportional to the product of the charges. That is, a force is directly proportional to the product of charges and inversely proportional to the square of the distance around them or between them, where Q1 and Q2 are the magnitudes of the two charges respectively, and R is the distance between them. The magnitude of the electrostatic force between 2 point-like charges is given by Coulomb's law. All right, folks. So there are some two important things that I want us to take out of this thing, right? The first thing is that the force between charges is influenced by two things. Firstly, it's the magnitude of the charges themselves. And number two is the distance between charges, right? So those two things influence the force, the force that we're talking about here. Now let's look at the definition. And by the way, this definition, you must know it. And you must know it in such a way that if a question comes and they want you to state Coulomb's law, you ought to be able to do so. Coulomb's law states that the magnitude of the electrostatic force between 2 point charges is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. All right, so this is the formula. And the proportionality constant is called the electrostatic constant and has the value of 9.0 times 10 to the 9, right, Newton meters squared per coulombs squared in free space. Now, similarity of Coulomb's law to Newton's universal law of gravitation, right? You'll see that between those two formulas, there are some similarities. Notice how similar in form Coulomb's law is to Newton's law of gravitation between 2 point-like particles. Now, this is the formula where M1 and M2 are the masses of the 2 point-like particles. D is the distance between them, and G is the gravitational constant. Both are inverse square laws. Both laws represent the force exerted by particles, right? Point masses or point charges on each other that interact by means of a field. Now let's look at some worked examples. 2 point-like charges carry charges of 3 times 10 to the negative 9 coulombs and negative 5 nanocoulombs are 2 meters apart. Determine the magnitude of the force between them and state whether it is attractive or repulsive. So step number 1, we must determine what is required. We are required to determine the force between 2 point charges, given the charges and the distance between them. And step number 2, to try and find an approach to this, we can use the Coulomb's law to calculate the magnitude of the force. Then step 3 is to determine what is given there. And then from that, we can then draw a diagram just to make the problem much more easier to comprehend. And then, now that all quantities are in SI units, then we can find the magnitude using the formula. Thus, the magnitude of the force is 3.37 times 10 to the negative 8 newtons. However, since the point charges have opposite signs, the force will be attractive. Then we can draw a free body diagram to show the forces. Each charge experiences a force with the same magnitude and the forces of attraction. No, each charge experiences a force with the same magnitude and the forces are attractive. So we have this. Okay, next is another example that demonstrates the difference in magnitude between the gravitational force and the electrostatic force. Okay, so determine the magnitudes of the electrostatic force and gravitational force between 2 electrons that are 10 to the negative 10 meters apart, meaning the forces felt inside an atom, and state whether the forces are attractive or repulsive. So we are required to calculate the electrostatic and gravitational forces between 2 electrons at a given distance apart. We can use this formula, right, to calculate the force between the electrostatic force between those particles, right? And then to calculate the gravitational force, we will use this one. Okay, so now some important things to remember. The charge of an electron is 1.6 times 10 to the negative 19 coulombs, and the mass of an electron is 9.1 times 10 to the negative 31 kilograms. It's a very small thing. And then the distance is 1 times 10 to the negative 10 meters. And we know these two constants, right? And with that being said, then we can draw our situation, then do some calculations. So this is the electrostatic force, and the magnitude of the electrostatic force between the electrons is 2.30 times 10 to the negative 8 Newton. Now, since electrons carry like charges, the force is repulsive, right? Then the gravitational force is 5.54 times 10 to the negative 51 newtons. You can see that thing is very small. The magnitude of the gravitational force between the electrons is that. Now notice that the gravitational force between the electrons is much smaller than the electrostatic force. Much, much smaller. Now let's look at some few tips. We can apply Newton's third law to charges because two charges exert forces of equal magnitude on one another in opposite directions. Now, when substituting into the Coulomb's law equation, one may choose a positive direction, thus making it unnecessary to include the signs of the charges. Instead, select a positive direction. Those forces that tend to move the charge in this direction are added, while forces acting in the opposite direction are subtracted. All right, question 3 or example 3. 3-point charges are in a straight line. Their charges are Q1, 2 nanocoulombs, Q2, 1 nanocoulomb, and Q3, -3 nanocoulomb. The distance between Q1 and Q2 is 2.2 times 10 to the -2 meters, and the distance between Q2 and Q3 is 4 times 10 to the -2 meters. What is the net electrostatic force on Q2 due to the other two charges? Here's a diagram just to help you understand the question. All right, so we need to calculate the net force on Q2. This force is the sum of the two electrostatic forces, the forces between Q1 on Q2 and Q3 on Q2. Now we need to calculate the two electrostatic forces on Q2 using Coulomb's law. We then need to add up the two forces using our rules for adding vector quantities, because force is a vector quantity. Since we are given all the charges and all the distances, we can now calculate the force on Q2 due to Q1. And if we do that, we should get 4.5 times 10 to the -5 Newton. Yeah. And then the force on Q2 due to Q3 is 1.69 times 10 to the -9 newtons. And now let's look at vector addition of forces. We know the force magnitudes, but we need to use the charges to determine whether the forces are repulsive or attractive. It is helpful to draw the force diagram to help determine the final direction of the net force on Q2. We choose the positive direction to be to the right. The force between Q1, the force between Q1 and Q2 is repulsive. This means that it pushes Q2 to the right or in the positive direction. The force between Q2 and Q3 is attractive. Those are unlike charges, and pulls Q2 to the right. Therefore, both forces are acting in the positive direction, right? Therefore, the sum of those forces is 6.19 times 10 to the -5 newtons. And this resultant force acts to the right. All right, now let's look at worked example 4. 3-point charges form a right-angled triangle. Yeah. Their charges are Q1, which is 4 nanocoulombs, Q2, 6 nanocoulombs, Q3, -3 nanocoulombs. Their distances are given. Now, what we're trying to find is the net electrostatic force on Q1 due to the other two charges if they are arranged as shown. So if they are arranged this way. Now, what is important, something that I want you to consider, is that if you look at -3, right? -3 is negative. Q3 is negative, and Q2 is positive, and Q1 is positive. So if I were to use the Cartesian plane, right? If I were to use my Cartesian plane, remember that, let's see, thing is I'm thinking of something here. No, sorry about that. Let's continue. Determine what is required. We need to calculate the net force on Q1. This force is the sum of the two electrostatic forces. The forces of Q2 on Q1 and Q3 on Q1. We need to calculate using Coulomb's law the electrostatic force exerted on Q1 by Q2 and the electrostatic force exerted on Q1 by Q3. We then need to add up the two forces using our rules for adding vector quantities because force is a vector quantity. We are given all the charges and two of the distances. The magnitude of the force exerted by Q2 on Q1, which we will call F2, is 8,630 times 10 to the negative 5 newtons. And then the magnitude of the force exerted by Q3 on Q1, which we will call F3, is 1,199 times 10 to the negative 4 newtons. Then, vector addition of forces. This is a two-dimensional problem involving vectors. We have already solved many two-dimensional force problems, and we will use precisely the same procedure as before. Determine the vectors on the Cartesian plane. Break them into components in the X and Y direction. Oh yeah, this is what I was thinking about. And then some components in each direction to get the components of the resultant. We choose the positive direction to be to the right, the positive X direction, and up the positive Y direction. We know that the magnitudes of the forces, but we need to use the signs of the charges to determine whether the forces are repulsive or attractive. Then we can use a diagram to determine the directions. The force between Q1 and Q2 is repulsive because those are like charges. This means that it pushes Q1 to the left or in the negative X direction. The force between Q1 and Q3 is attractive and pulls Q1 in the positive Y direction. We can redraw the diagram as a free body diagram, illustrating the forces to make sure we can visualize the situation. Okay, this is our situation. Okay. Then to find the resultant force, the magnitude of the resultant force acting on Q1 can be calculated from the forces using Pythagoras theorem because there are only two forces and they act in the X and Y direction. Okay. So the resultant force will then be 1,48 times 10 to the negative 4 newtons. And then the angle made with the x-axis can be found using trigonometry, right? Remember that the angle can be found using tan theta because tan is the opposite right side over the adjacent side to the angle, right? Sure. Okay. Now, why did we use? Okay, anyway, if you do that, then you can see that actually we have our angle as 54,25 degrees. And the final resultant force acting on Q1 is 1,48 times 10 to the negative 4 Newton, acting at an angle of 54.25 degrees to the negative x-axis, or 125.75 to the positive x-axis. We mentioned in grade 10 that charge placed on a spherical conductor spreads evenly along the surface. As a result, if we are far enough from the charged sphere electrostatically, it behaves as a point-like charge. Thus, we can treat spherical conductors, e.g. metallic balls, as point-like charges, with all the charge acting at the center. So please, folks, pause the video and try these exercises. Folks, I hope that you really tried all those exercises. I mean, even if a question was difficult, at least try it. And then if you can't do it, skip it, right? So let's look at some solutions together. So for number one, the force is 1.35 times 10 to the negative 2 newtons between those particles. And then this force is repulsive since it is between two like charges. And then for number two, the force is 1.27 times 10 to the negative 3 newtons. And this force is repulsive since it is between two like charges. Then number three, the force is 0.26 newtons. This force is attractive since it is between two unlike charges. All right. Something important. The distance is given as centimeters here. So you ought to remember that the SI unit for distance is meters. So you must convert your centimeters to meters. All right. Sure. Then for number four. So for number four, 2-point charges exert a 5 Newton force on each other. What will the resulting force be if the distance between them is increased by a factor of 3? Now let the charges be Q1 and Q2. For the first situation, we have this, which is the original, right? Now we increase the distance by a factor of 3. So we get that if we increase it by a factor of 3, we basically have 9r squared. And 9r squared is going to be 9. Man, you have 3r to the power of 2. Then 3 squared is 9. Then r squared is r squared. We now note the following, that F, the force times r squared is equals to Q, K, Q1, Q2. And now we have Fe2, 9r squared equals to K, Q1, Q2. Therefore, Fe2, if we equate those two things, we're going to see that Fe2 is equals to 0.56 newtons. Nah. Sure. So we basically used the original situation, and then We created the second situation that was given. Then we equated those two and to find the solution. For number 5, 2-point charges are brought closer together, increasing the force between them by a factor of 25. By what factor was their separation decreased? Again, this is situation number 1. Now it decreased by an unknown factor. We'll call it x. And the distance we get is xr squared. We now note the following, that Fe2 is equals to 25 kq and y25 because we increase by a factor of 25. Sorry. Therefore, if we equate those two situations, x is equal to 0,2. Number 6. If two equal charges, each of 1 coulomb, are separated in air by a distance of 1 kilometers, their magnitude is just 9,000 newtons. This force is repulsive since it is between two like charges. You should notice that even at a distance as large as 1 kilometer, the repulsive force is substantial because 1 coulomb is a very significant amount of charge, very big. 7. Now for this one, you just have to make D the subject of the formula. And if you do that, you get 4,6 times 10 to the negative 3 meters. Number 8, we first calculate the force on Q2 from Q3, and we get 1 times 10 to the negative 1 Newton. And then we calculate the force of Q1 on Q2. Note that for this force, we must add R1 and R2. So we do that, and then we get that. All right. And I hope you understand why we added R1 and R2. Right, because this whole distance separate the two charges. Next, we know that the force of Q3 on Q2 is repulsive and the force of Q1 on Q2 is also repulsive. So these two forces act in the same direction towards the right. The resultant force is therefore the sum of those two, which is 8,77 newtons to the right. Then for number 9, we are told that the resultant force is 6.3 times 10 to the negative 5 newtons to the right. Since the force of Q1 on Q2 is attractive, the force of Q3 on Q2 must be repulsive to cause a resultant force to the right. If it was also attractive, the resultant force would be to the left. So we know that Q3 must be negative. So we first calculate the force on Q2 from Q1, and that is 0.51 newtons. Next, we use this and the resultant force to find the force on Q2 from Q3. All right, so the resultant force is 0.12 newton. The resultant force is equal to F1 plus F2. And so F2 is equal to 0.12 newtons. And then we calculate the charge on Q3. Right. Now, if you do that, then we get our Q3 as being 4.2 times 10 to the negative 8 coulombs. Then for number 10, we first calculate the force on Q1 from Q2, get it, and then we calculate the force of Q3 on Q1, and we get it as well. Then the magnitude of the resultant force acting on Q1 can be calculated from the forces using Pythagoras theorem because there are only two forces and they act in the x and y direction. We can find the angle using trig, right? Then your angle should be 83.3. The final resultant force acting on Q1 is 3.42 times 10 to the negative 5 newtons, acting at an angle of 83.8 to the negative x-axis. Calculate the resultant force on Q1 given this charge configuration. We first calculate the force on Q1 from Q2. And then that's the force. Then we calculate the force on Q3 of Q3 on Q1. Then that's what we get. Then from there, it's the magnitude using Pythagoras theorem. After getting the magnitude, we now try and find the angle there, which gives us the direction. Okay, then number 12. First find the force. Okay. Yeah. The final resultant force acting on Q1 is 1,05 times 10 to the negative 4 newtons, acting at an angle of 34.76 to the positive x-axis. All right, folks, thank you so much. That's it for today. Tango.